Now that we have a good understanding of relations and functions, we're now going to start to talk about our very first type of function, which is called a linear function. A linear function is exactly what its name says. It is, when graphed, the shape of a line. Okay. Now, specifically, when we look at the inputs and outputs, what you're going to see is what's called a constant rate of change between your inputs and your outputs. Constant rate of change means that the values are going to go up or down by the same amount every time. Because of that, when you graph it, it's going to form a straight line whether going upward or a straight line going downward. Compared to anything that is not a linear function or a nonlinear function will not have a constant rate of change, and therefore when you graph it, it will form some sort of curve. Now, when written, a linear function is always going to be of the form y equals mx plus b, where in this form, m and b are going to represent two numbers. So for example, y equals, let's say, 2x plus 1. So this would be considered a linear function. One way to recognize from its form that this is a linear function is by considering the input. So the input in any function, again, is always going to be x, where the output's going to be y. In a linear function, what you're going to see is some basic mathematical operations attached to x, our input. So for example, here I have 2x, which represents multiplication, and then you'll see here at the end plus 1. Some very basic operations there of multiplication and addition. I can do the same thing with division and subtraction, or a combination of the like. A nonlinear function, what you're going to see are different things such as exponents. I might have my input being raised to some power, like say to the second power or to the third power or whatever power it might be. I can reverse that and maybe have a base taken to where my input is now the actual exponent. I might see like square roots of certain values. So when I start to see some different mathematical operations here, exponents, roots, those are going to be nonlinear functions. So a linear function is always going to look of this form. Okay, and this form again is some basic mathematical operations of multiplication, division, adding, and subtracting. So what we're going to do is we're going to look at a couple examples here of how to recognize if something is linear or nonlinear. First way, the easiest way to do it is to look at it as a graph. A graph, again, is a visual representation of a function. You have on any sort of graph the horizontal axis, which is known as the x-axis. Those, again, represent our inputs. And then you have the vertical axis, which goes up and down. That is the y, and y, again, is going to represent our outputs. So when we plot a graph, essentially what we're doing is we're plotting points. So it's not really shown explicitly here, but you have different points on this graph that we can then look at the overall relationship. A linear function, when you plot those points, will form a line. So obviously this first one is a nonlinear function because it is forming a curve. Whereas the second one, if I were to plot points here on this graph, you will see that those points form a straight line. So this would be considered a linear function. Now in terms of the points themselves, you'll notice that as we go from point to point, key thing that makes it a linear function is it's a constant rate of change. So what you will see here is that as we go from point to point, recognize that we are going up 2 over 1 every time. Up 2 over 1, up 2 over 1, up 2 over 1. That is what's meant by a constant rate of change. Compared to the curve, I would go up 1, right 1, up 3, right 1. Notice that is not a constant rate of change. Okay, so now let's do the same thing from a table. So from a table, what we're going to have to look at is that idea of a constant rate of change. I'll put it as ROC, rate of change. So when I look at a table, what I'm going to do is I'm going to first look at my x values. So my x values, again, are going to represent my inputs. So in this first example, I have 3, 6, 9, and 12. So you'll recognize here that this would be plus 3 every time, which is good because that's constant. But what's really going to determine whether it's a linear function is not our inputs, but our outputs. What I want to see is that I have a constant rate of change between my outputs. Asking then, how do I get from each of my outputs? So 36 down to 30 to 24 to 18. Recognize there that I would be going down 6 every time. So since it's subtracting 6 and that's constant, meaning it's not changing, this would represent a linear function because, again, it is a constant rate of change. Whereas in number 2, or in example B, if I look here again at my my inputs, my x's, you'll still notice here again that it's going up by 2. So that's a constant rate of change. But when I look at my y values again, my outputs, 2, 9, 20, and 35, when I track their change, 2 to 9 would be plus 7. This would be plus 11. That would be plus 15. So recognize that that is not a constant rate of change, so this would be non-linear. And then lastly, let's recognize linear functions through equations. So this is again of the form. So I mentioned before, when defining linear functions, all linear functions are going to look of this form. Y equals mx plus b, where again, m and b are going to be numbers. So first of all, in the first example, 2x plus 1, you will recognize that this is of the form mx plus b. So right away, I can see that this is linear. In example B, you'll recognize here that I have an x to the second power. So one thing I talked about is that anytime you see exponents or any other mathematical operations that are not multiplication, division, addition, or subtraction, that means that this function would be non-linear because of that x squared. Same thing in example C, I see 2 to the x power, so instead of raising my input to some power, I'm raising some number to my input. A little bit different, but the idea here that this would also be nonlinear. Last example, you'll notice 6 times x minus 1. I have parentheses here. Now, this one's a little bit tricky because of its form. It doesn't look correct. However, parentheses are a way to simplify multiplication. So just to finish this off, if I were to say distribute that 6, I would get y equals 6x minus 6. And now recognize that this is of the form y equals mx plus b. The only difference is that instead of adding, I have subtracting going on. But nevertheless, this would be considered a linear function because it's of the correct form, written the right way. So now we're able to recognize linear functions through graphs, tables, and equations. Now let's talk about the whole idea of inputs and outputs. So again, any sort of function where we have y equals, let's say, a linear function mx plus b, where again my m and b are just going to be numbers. But all functions are going to be written in terms of inputs, which are my x values, and outputs. And the idea is when any function is what you plug in and what you get out. So what we're going to focus on now are the things that we can plug in. We introduced a term in our first section, the term domain. Domain, again, if you remember, is a set of all the inputs in any sort of function. And I actually mentioned this in the first lesson that we did. There's 2 types of domains that we can consider when plugging in values. We can consider what's called a discrete domain. A discrete domain is when our set of inputs consists of only whole number intervals. So for example, here you'll see discrete points, 1, 2, 3, 4, all the way up to 5. What that means is that I am looking at specifically the value of 1 at the value of 2, but I am not considering any value in between them. That would make sense to only describe things in terms of whole number values. The analogy I gave to you guys was like a coin machine. I can only plug in whole number of dollars. I can plug in $1, $2, and get change out of it. I can't plug in $2.10 and expect to get quarters out of that. It's whole values of dollars to get whole number of quarters. And that compares to the other way to describe a domain, which is called continuous. Continuous means the opposite of a discrete, is that instead of having 2 points without having any values in between, continuous considers all the values in between 2 set numbers. So for example, here you're shown 2 points at 1 and 5, and you'll notice that there's a line connecting them. So what I'm looking at here is all the values between 1 and 5. I'm not only looking at the whole numbers of 2, 3, and 4, but I'm considering any sort of decimal or fraction between those. I can consider 1.5, 2.5, maybe 2 3/4, whatever it might be. I'm looking at all the values from 1 to 5. Written, if you remember, we look at our low value of 1 and our high value of 5. And what I'm trying to say is that all of my values, written as a compound inequality, all of my inputs would be between 1 and 5, and that would be considered continuous. So now let's apply this idea of not only linear functions, but the idea of continuous versus discrete domains. So here we have a linear function y equals 12x. So again, y represents our output, x represents our input. It says here that y represents the cost in dollars of x number of tickets. So y is going to represent the number of dollars, and x is going to represent the number of tickets I purchase. Okay, so what that function represents, that if I were to purchase, let's say, 1 ticket, it's going to cost me a certain number of dollars. And the function says 12x. So 1 ticket would cost $12, 2 tickets would cost a certain number of dollars, and so on and so on. And it says here that each customer can buy a maximum of 4 tickets. So first thing I'm going to do is try and understand my domain. Excuse me. So domain is going to be, again, the set of inputs. What are the things that I could potentially plug in to this equation where x goes? So based on what you're given, it says that each customer can buy a maximum of 4 tickets. So the possibilities is I could buy no tickets, I could buy 1 ticket, I could buy 2, I could buy 3, or I could buy 4. Notice that when I think about this, that I'm representing the number of tickets in terms of whole numbers. It does not make sense to buy 2.5 tickets. Okay, I have to buy a whole number of tickets. So because of that, this would represent what's called a discrete domain, because I'm looking at the whole number values there. Now, my goal then is to take these inputs and figure out then the outputs so that I'm able to graph them. So to take that, or to figure out the outputs, my outputs, y, can be found by taking my function of 12x and taking all of my inputs and plugging them in where x goes. Now when I see 12x again, that means I'm multiplying. So for example, if I take 0 times 12, that would give me 0. 1 times 12 will give me 12. 2 times 12 will give me 24. Then 36, and then lastly 48. Then what I can do is imagine each of these as my inputs and outputs as points on a graph. So points on a graph, it would be, for example, 0, 0, 1, 12, 2, 24, 336, and 448. So then on my graph, I can plot these as points, understanding that my inputs are on my x-axis and my outputs are on my y-axis. So I'm going to plot these points real quick. And what you will recognize that when plotting those points, notice they form the shape of a line. Okay? Now, if I were to draw the line through this again, you can see that it's going to form that shape. However, because this is a discrete graph, I do not want to draw the line connecting these points. I'm just going to draw this as a set of points, because it does not make sense if I were to connect this with a straight line. It does not make sense to buy a half of ticket for half the price, or 1.5 tickets for half that price. So I'm going to represent this linear function as discrete points on a graph. All right, in the next example, we'll do the same idea. Okay. Now here it says a car is driving at a rate of 50 miles per hour. It says the number of miles is a function of the number of hours driven. And I want to know, does this situation represent a linear function? So it says that it's driving at a rate of 50 miles per hour. So key thing here, 50 miles per hour. Now I want to know, is this a linear function? So 50 miles per hour, you can think about what that means. 50 miles per hour means that I'm going to go, let's say, in 1 hour, I would go 50 miles. In 2 hours, I'd go 100 miles. In 3 hours, I'd go 150. In 4 hours, I'd go 200, and so on and so on. So does this represent a linear function? So remember, a linear function always has a constant rate of change. Considering the outputs I get, I go from 50 to 100, which means I'm adding 50, 100 to 50, 100 to 150, 150 to 200, and so on. And notice that every time I'm just simply adding 50. That's what 50 miles per hour means. At every hour, I would go 50 miles. So notice that is a constant rate of change. So is this a linear function? Yes, most definitely it is, because we have a constant rate of change between my outputs. Now it says here in the next part, I kind of did this already, but it says here to find the domain of the function, and I want to know, is this domain discrete or continuous? So I'm going to start with this in terms of discrete or continuous. So notice here that when I'm thinking about the problem that I chose 1, 2, 3, and 4 as the number of hours that I had, okay? Now, for a car driving, a car can drive from, let's say, 0 hours, which I didn't include, which you would drive 0 miles, drives all the way up to 1 hour. Now, when you go from 0 to 1 hour, you got to think to yourself, when I'm driving, if I go from 0 to an hour, I've driven 15 minutes, I've driven an hour, or sorry, half hour, I've driven 45 minutes, I've driven 47 minutes. So when you're driving, when you're thinking about time, time is something that's continuous. The number of hours on a clock, when you track time, that second hand goes, that minute hand goes. So in this case, this is going to be a continuous function. Ooh, sassy, okay? Now, if it's continuous, then that's going to affect how we think about our domain. I looked at my domain as discrete values here, but I have to think about that my domain is going to be including all of the values in between those whole numbers. Now, because we're talking about the number of hours, there is one restriction. I cannot have the number of hours go into the negative realm of my numbers. So the number of hours is going to start from 0, and then I can drive as long as I want. So what I'm really looking at is my inputs are going to be from 0 and any number beyond that. So what I'm going to do is I'm going to write this as an inequality. Now this one's going to look a little bit different, but based on what I said, my inputs are going to be anything greater than or equal to the number 0. Now, why am I not including this? Why am I not writing this like I did before, where I had a number, boom, boom, x, and then boom, boom, another number? Is because there is no limit to this side right here. Okay, I can drive as many hours as I want. I can, as long as I had enough gas, I could continuously drive forever and ever and ever. So essentially, the number of hours can be anything greater than 0. So on my graph, I'm going to start off by plotting a point at 0, 0. And then I'm just going to track this. We have then 50, 100, 150, 200, 250, 300, 350, and so on. Notice that when I plot those points, it forms a straight line. But because this is continuous, I'm now going to connect those points with a smooth line. And I'm going to draw an arrow at the end to represent that this relationship could continue on forever and ever. All right, so again, this was ending by looking at the idea of discrete and continuous, but the overall idea was looking at linear functions, recognizing them from graphs, tables, formulas, and then understanding the idea of domains as continuous or discrete based on what I can plug in. So if you got any questions, jot those things down. Otherwise, see you next time, folks.